High purity copper is obtained by electrolysis using a thin pure copper cathode and an acidified solution of copper sulfate, clearly demonstrated on our schematic. And then 9.1 says, at which electrode will pure copper be deposited? Write only A or B. So back to the basics again. In electrolysis, we have two electrodes connected to a power source, right? Clearly, this will be the positive terminal and this will be the negative terminal. Now, the question you have to ask yourself is that which electrode is connected to the positive terminal and which electrode is connected to the negative terminal? In an electrolytic cell, the anode will be connected to the positive terminal. So here we know that electrode B is our anode, and then consequently electrode A is our cathode. But that's not what the question is asking us. At which electrode will pure copper be deposited? Write only A or B. Where the pure copper is deposited, it's where reduction happens, the gaining of electrons that takes place at the cathode, right? So from that information, here our answer would be A, right? That's where the pure copper will be deposited because A is our cathode and that's where reduction takes place. And then 9.2 says, write down the half reaction for this cell. We have pure copper. It needs to be deposited somewhere. We're saying that it takes place at the cathode, and at the cathode, that's where reduction takes place. So we're going to have copper 2 plus 2 electrons, giving us copper. That's our reduction half reaction for this cell. Now let's move to 9.3. 9.3 says that use the graph to calculate the percentage purity of the impure copper that was used as the cathode. The mass of the impurities formed in an hour is 15.8 grams when a constant current is used. Right, now let's go back to the basics. We have percentage purity, right? Percentage purity, that is mass of pure sample, right? Divided by the mass of the impure multiplied by 100. But in this question, it's not really that clear, so we have to break it down, right? The mass of the pure sample will be the mass deposited at the cathode, right? So here we're gonna have mass deposited, and then mass of impure will be mass deposited plus the impurities that are left behind, right? So here we have mass deposited plus the mass of the impurities, right? Multiplied by 100, because we have this chunk of an impure sample, and then some of that amount gets deposited at the cathode, so we know that that amount is pure. But then the mass of the impure sample as a whole will be the mass of the impurities plus the mass of the deposited. So we are told that after an hour 15.8 grams is deposited at the cathode, right? So we're gonna have 15.8 divided by 15.8 mass deposited plus the mass of the impurities. The mass of the impurities formed in an hour is 15.8 grams, right? So we're basically gonna be finding mass deposited. So we're gonna have mass deposited, which we're going to find divided by 15.8. That is for impurities, right? Plus mass deposited again. So we have mass deposited. We're still multiplying this entire number by 100. So now our duty is to find the mass deposited, right? If we go back to our sketch here, you're gonna see that the number of moles deposited in 1800 seconds is 0.25, right? But then here on our equation, we're given the mass of impurities in an hour, right? So we have to multiply this 0.25 to find the number of moles deposited in an hour, right? We have the impurities in an hour. We have to find the number of moles in an hour. So now we can say that the number of moles is equals to mass divided by molar mass. So we're looking for the mass, so we're gonna say the number of moles multiplied by the molar mass. So what is the number of moles? The number of moles in an hour will be 0.25 multiplied by 2, right? We are given the number of moles in 30 minutes. We want the number of moles in an hour, so we simply multiply by 2, right? And then the molar mass, we're looking for the molar mass of copper, which is 63.5, and then when you multiply that 2, you get 31.75 grams, right? Our percentage purity, right, will then be equals to 31.75, which is the mass deposited divided by 15.8, which is the mass of the impurities, plus the mass deposited again, which is 31.75 multiplied by 100. And then if you punch that in your calculator, and that will give you 66.67%. Now let's move forward to 9.4. 9.4 says the copper sulfate is an electrolyte and the concentration remains constant for the duration of the reaction. 9.4.1 define an electrolyte. An electrolyte is a solution that conducts electricity through the movement of ions. An electrolyte is a solution that conducts electricity through the movement of ions. And then 9.4.2 says explain why the concentration of the solution remains constant. The concentration of the solution remains constant because the rate of oxidation is equal to the rate of reduction. The rate of losing electrons is equal to the rate of gaining electrons, and as a consequence, the concentration of the solution remains the same.
Write down the energy conversion that takes place in this cell. It is an electrolytic cell, so we have electrical energy to chemical energy, electrical energy to chemical energy. We can also see that by the presence of a power source, we have electrical energy being supplied to the cell, and that electrical energy is then converted to chemical energy. 9.1, let's take a look at 9.2. At which electrode A or B will pure copper be deposited? 9.2. Right, so pure copper, it will get deposited at the negative electrode, meaning that the answer to 9.2 should be B. Let me show you why it will get deposited at the negative electrode. Take a look at this. We have CuCO4, which will break down to form copper 2 plus SO4 2 minus. This is a positive ion. This is a negative ion. The positive ion will get attracted to the negative electrode, which is B, and that's where a reduction is going to take place. So that is why I'm saying that the pure copper will be deposited at the B, because it is negative, and the copper 2 plus will be attracted to the negative electrode as positive and negative attracts. 9.2. Let's take a look at 9.3. Write down the half reaction that takes place at the anode. At the anode, we have oxidation of copper, right? So we're going to have copper turning to copper 2 plus 2 electrons at the anode. This is at the electrode A. At the electrode A, we're going to have copper becoming copper 2 plus 2 electrons. There we go. Let's take a look at 9.4. How will the gradient of the graph be affected as the reaction is allowed to proceed until completion? Right, only increase, decrease, or remain the same. So let's take a look at what's happening here. in more detail. The diagram below represents the purification of copper ore to pure copper. The cell also contains zinc, silver, and platinum impurities. Right. The graph shows the initial relationship between the mass of copper deposited versus the time. So back to our question, how would the gradient of the graph be affected as the reaction is allowed to proceed until completion? Well, the gradient of the graph is not going to change. The gradient of the graph is not going to change. As oxidation occurs, reduction occurs. So we're never going to reach a point where the mass of copper deposited, well, the rate at which the mass of copper deposited goes down, we're never going to reach such a point or a rate where it increases. The gradient will remain the same throughout until completion. Right. 9.5. Refer to the relative strength of reducing agents to explain why zinc will not be deposited at the cathode. Why zinc will not be deposited at the cathode. Why zinc is not going to be deposited at B. So let's take a look at what is happening here. The question says that we have some impurities, which happens to be zinc, silver, and platinum. But in our question, we are only interested, so let me just say in 9.5, we are only interested on zinc and copper. Why is zinc not being deposited at the cathode? Why is it copper that is being deposited at the cathode? So it means that we have, as our ions in the solution, we have zinc 2 plus and copper 2 plus. One of these two is to be deposited at the cathode where reduction is going to take place. So between zinc 2 plus and copper 2 plus, what is the stronger oxidizing agent? Because the stronger oxidizing agent is what's going to get deposited at the cathode. The stronger oxidizing agent is what's going to get deposited at the cathode. So what do we need to do? We need to go to a predict table and see which one it is between zinc 2 plus and copper 2 plus. The question says, why is zinc not being deposited at the cathode? So obviously we already have our answer, but I'm just trying to show you where it is coming from. Copper 2 plus is a stronger oxidizing agent compared to zinc 2 plus. Let's go to our table so that it can be easy to see. All right. So our table, standard reduction potential. Okay, let's take a look at, let's use 4A. It doesn't really matter which table we use, by the way. So take a look. Increasing oxidizing ability as we go down. So let's look for zinc and copper 2 plus. Okay, so where is zinc? Where is copper 2 plus? This is copper plus. We're not looking for that. We're looking for copper 2 plus. We have copper 2 plus right here. No, that is actually not the one we're looking for, because we're looking for the one that will accept 2 electrons to form copper. This is the one we are looking for. This is the copper 2 plus you're looking for. So be very careful when you're using this table. You just don't find copper and take it as it is. You have to take a look at exactly what you are dealing with. Okay, so we're saying that copper 2 plus is a stronger oxidizing agent. So we must find zinc. I was starting to get worried a bit. Here we have a zinc 2 plus, but look at my arrow. My arrow is going the wrong direction. The arrow is supposed to be pointing up, as you can clearly see here on our table. So clearly, copper 2 plus is a stronger oxidizing agent compared to zinc. So the answer to 9.5, which is saying refer to the relative strength of reducing agents to explain why zinc will not be deposited at the cathode. Zinc will not be deposited at the cathode because copper 2 plus is a stronger oxidizing agent, right? And zinc 2 plus is a stronger reducing agent. Therefore, okay, so that is the reason why it is copper 2 plus that's going to be deposited at the cathode and not zinc 2 plus. Okay, that is 9.5. Let's take a look at 9.6. Maybe I need to erase this going to 9.6 so that I can have a bit of space. So let's do that. Back to our diagram and back to 9.6. So 9.6, When the current flows for 30 minutes, 15 grams of copper was deposited at one of the electrodes. Okay, and then 9.6.1, calculate the number of moles of copper deposited. Well, quite an easy equation because we are given the mass. So we are really sticking to the basics. Number of moles is equal to the mass divided by the molar mass. Right, and then the mass is 15 grams. The molar mass of copper, that is 63.5. When you put that in your calculator, you get 0.24 moles. Right, it's quite a strange equation, right? Because we're just calculating the number of moles, no trickery whatsoever. 9.6.1, let's take a look at 9.6.2. Determine the number of moles of electrons that flows through the circuit while 15 grams of copper is deposited. 1 mole of copper gives us 2 moles of electrons. Right, it sounds very wrong to say 2 moles of electrons, but we can see the relationship here. For 1 copper atom, we have 2 electrons. So if we're saying that the number of moles of copper, well, we're saying copper is 2 electrons. If we're saying it is 0.24, then that of electrons should then be 0.48 moles. So there we go. That is question 9. In electrochemical cell A, we have carbon as the electrode, while in electrochemical cell B, we have copper as the electrode. The first question, 1.1, are A and B electrolytic or galvanic cells? It will be easy to see that A and B are electrolytic cells. Why do we say so? The presence of a power source and the mere fact that both electrodes are in one container. In a galvanic cell, the electrodes are in different containers and there is no power source. 1.2, which of the electrode P, Q, R, or T will show a mass increase? Write down a half reaction to motivate the answer. In both galvanic and electrolytic cells, we see a mass increase at the cathode. The only difference is that in a galvanic cell, the cathode is positive, while in an electrolytic cell, the cathode is negative. If you look at electrochemical cell A, Q is the negative electrode and T is the negative electrode. So that is where we expect to see a mass increase. So the answer here is Q and T. Why is there a mass increase at the cathode? That is because copper 2 plus is getting reduced to copper. More on this in the following question, 1.3. I'm going to explain why that is so. But for now, let's just leave it like that. Let's go to 1.3. So in 1.3, we're supposed to write down the name or formula of the product formed at electrode P. So let's go ahead and take a look at electrode P. P is the anode and Q is the cathode. So we have P being our anode and Q being the cathode. This is probably the most important part of the video. This is exactly what I want you to learn. We know that N ions move to the anode. What are N ions? Negative ions. In our case, the negative ions we have is Cl minus. Why am I saying Cl minus? This is coming from CuCl2, the electrolyte we have. It is an aqueous solution and not liquid. So we also have OH minus from H2O. And then the cat ions, positive ions, that will move to the cathode. We have Cu2 plus and H plus. The question here now is between Cl minus and OH minus, what undergoes oxidation? Cl minus is going to undergo oxidation. The only way OH minus would go under oxidation is if instead of using concentrated Cl2, we use dilute. And another special case is when we have SO4 2 minus or NO3 minus as the other N ion. If this is the case, then OH minus will get oxidized. But if these conditions are not satisfied, then Cl minus or any other N ion will get oxidized. So at the anode, we have 2Cl minus getting oxidized to form Cl2 plus 2 electrons. The product that is formed at electrode P is chlorine gas, or Cl2, if you decide to write the formula. Let's go ahead and do 1.3.2. We're looking for the name or formula of the product formed at electrode R. Electrode T is the cathode, so electrode R is our anode. What N ions are we going to have at the anode of electrochemical cell B? This is where it gets interesting and gets complicated. At the anode, we have copper as our electrode. So the species we're going to have is going to be copper, Cl minus, and OH minus. The question really here is between copper and Cl minus, what gets oxidized? Copper is a stronger reducing agent compared to Cl minus, so copper will get oxidized. We're going to have copper getting oxidized to form copper 2 plus 2 electrons. So the product at electrode R is actually copper 2 plus and not chlorine. Now I want us to go back to 1.3.1. If you look at 1.3.1, we talked about why Cl minus gets oxidized at the anode. Let's talk about the cathode. What will get reduced between Cu2 plus and H plus? What is going to get reduced there? It's Cu to the 2 plus. Why do I say so? Cu to the 2 plus is less reactive compared to H plus. The question now is, how do I know which species is less reactive compared to the other species? Well, the description of the video, I'm going to put the species from the least reactive to the most reactive. So make sure that you check that out in the description. This is quite a unique and special question, more especially when you take a look at 9.2.3. We're supposed to calculate the value of X as shown on the graph for 6 marks. What is the information we have? We have the current, which is 2.5 ampere, and the time, which is 10 hours. How do we go from current to time to X on the graph, which is basically the mass of the electrode? Well, you're about to find out. The first question, 9.1, we are supposed to define the term electrolysis. That is the use of electrical energy to produce a chemical change. The use of electrical energy to produce a chemical change. Usually, a lot of people will define it as a chemical process in which electrical energy is converted to chemical energy. That is also totally fine. That is 9.1. 9.2, on the other hand, the graph below, not drawn to scale, represents the changes in the mass of electrode T during electrolysis. We have the electrolysis of concentrated chromium chloride, CrCl3. We have 2 electrodes, R and T. The first question, 9.2.1, we're looking for the half reaction that takes place at electrode T. We have 2 electrodes, R and T. This is the mass. This graph is showing us the mass of the electrode T. As you can clearly see, the mass is increasing. And we know that the mass increases at the cathode. So T is our cathode and R is our anode. This is true for both galvanic cells and electrolytic cells. There is a mass increase at the cathode. So we need a half reaction that is taking place at the cathode. Okay, our electrolyte is CrCl3. The ions we have is Cl minus and Cr to the 3 plus. Those are the ions we have. But this CrCl3, it is an aqueous solution. So there's H2O. Apart from these ions, we also have OH minus and H plus. We know that N ions, they migrate to the anode, while cation ions migrate to the cathode. So that's why I have Cl minus and OH minus under the anode, and C to the 3 plus and H plus under the cathode. At the cathode, oxidation takes place. We're going to have oxidation of Cl minus, and at the cathode, reduction takes place. At the cathode, chrome 3 plus will undergo reduction. We can also see that from the net cell reaction that we are given. So the half reaction that will take place at electrode T, which is our cathode, will be Cr to the 3 plus 3 electrons to give us Cr. That is the half reaction that takes place at the cathode. 9.2.1. 9.2.2, a current of 2.5 ampere passes through the cell for 10 hours. Let's calculate the total charge that flows through the cell during this time. So we have the current, we have the time, we are looking for the charge. Which equation can we use? The current is the rate of flow of charge. So we're going to have the current being equals to the charge divided by the time. In order to find the charge, we can simply cross multiply and have the current 2.5 multiplied by time, multiplied by the time, which is 10 hours. But we know that our time is supposed to be in seconds. So we're going to have 10 hours multiplied by 60 minutes multiplied by 60 seconds. If you put that in your calculator, you're going to get 90,000 coulombs. This is the charge, the amount of charge that flows through the cell during this time. 9.2.2. The question you've been waiting for, 9.2.3. Let's find the value of x as shown on the graph. Well, what is the question really asking us to calculate? We know that we have chrome being deposited at the cathode. So we need to calculate the mass of the chrome that has been deposited at the cathode. How can we do that? Let's look at the information we have. We have the charge. How can we go from charge to number of moles essentially before we ultimately calculate with the molar mass and find the mass? From the charge, we can find the number of electrons. From the number of electrons, knowing fully well that 3 electrons will result to 1 chromium atom, we can determine the number of atoms of chromium. From the number of atoms of chromium, we can ultimately find the number of moles using Avogadro's number, and then we can determine the mass. Let's go ahead and do that. The number of electrons is equals to the charge divided by the charge of an electron. This will give us 90,000, which is the charge we determined above, divided by 1.6 times 10 to the minus 19. That is equals to 5.63 times 10 to the power 23 electrons. Let's use it to find the number of atoms of chromium. Well, 3 electrons will give us 1 atom of chromium. So we can say that the number of atoms of chromium is equals to the number of electrons divided by 3. We're going to have 5.63 times 10 to the power 23 divided by 3. If you put that in your calculator, you're going to get 1.88 times 10 to the power 23 as the number of atoms of chromium. Now we can use the number of atoms of chromium to find the number of moles of chromium. The number of moles is equals to the number of atoms divided by Avogadro's number. This will give us 1.88 times 10 to the power 23, everything divided by 6.02 times 10 to the power 23. This is equals to 0.31 moles. So we have the number of moles. We can go ahead and find the mass. The mass will be given by the number of moles multiplied by the molar mass. 0.31 multiplied by 52. That is the molar mass of chromium. If you put that in your calculator, you'll get 16.12. X is just equals to 16.12 plus 2.2. This will give us 18.32 grams. Besides concentration, write down 2 conditions needed for the hydrogen half cell to function under standard conditions. In total, we have 3 standard conditions, one being concentration at 1 mole per decimeter cube. 1.1, we're looking for the other 2 standard conditions. That is pressure. Pressure is one of our standard conditions at 101.3 kilopascals. Another standard condition we have is the temperature at 298 kelvins or 25 degrees Celsius. That is the answer to 1.1. Let's go ahead and take a look at 1.2. Give 2 reasons besides being a solid why platinum is suitable to be used as an electrode in the above cell. So as you can see here, where there is hydrogen gas, platinum is used as an electrode. Let's talk about why that is so. Hydrogen gas, as the name says, hydrogen gas. So it is a gas and we need our electrode to be a solid. But apart from platinum being a solid, what other properties does it possess? Platinum does not react with H+. So that is one of the reasons why it is being used as an electrode. And another reason is that platinum is a conductor. Platinum is a conductor. At 1.3, we're supposed to write down the name of component Q. This is a galvanic cell and component Q should be a salt bridge. So there we go. We have a salt bridge in 1.3.1 and 1.3.2. What is the standard reduction potential of the X half cell? Right, this is for 1 mark. And when you are familiar with this kind of questions, you're going to be able to answer it without any difficulties. But here we sort of have to take the long route so I can show you what is happening. Let's look at the information we have. We are told that the initial EMF that is registered is 0.31 volts. So the EMF of our cell initially is 0.31 volts. Right, now let's look at our setup. This is the positive electrode and this is the negative. In a galvanic cell, the positive is the cathode and the negative is the anode. So what are we saying? We're saying that the potential of our cell can be determined by saying the potential at the cathode minus the potential at the anode. So what is the potential of the cell? This is 0.31 being equals to the potential at the cathode. The potential at the cathode is the potential of the hydrogen gas, as we can clearly see that it is at the positive terminal. So we're going to have 0. If you look at your table for standard reduction potentials, the potential of hydrogen gas is 0 minus the potential at the anode. So minus the potential at the anode, which happens to be X. If you go ahead and find the reduction potential of X, you're going to realize that it is equals to minus 0.31 volts. So this is the answer. It is for 1 mark because it is easy to see without doing any calculation. But if you are not familiar with galvanic cells and the EMF of a cell, this is how we get to the answer. Right. 1.3.3, the half reaction that takes place at the cathode. The cathode is the positive terminal on our galvanic cell. So we have the hydrogen gas. The basics at the cathode is where reduction occurs. What is reduction? Reduction is the gaining of electrons. So we're going to have 2H plus 2 electrons to give us hydrogen gas. This is the equation you find on your table of standard reduction potentials. If this was the anode, then we would write the equation in the following way. We would have hydrogen gas giving us 2H plus 2 electrons if it was at the anode. If it is the cathode, if it is at the cathode and the reduction is taking place, then this is our equation. Right. I'm just doing that for the sake of clarity. When you have equation which requires the half reaction at the anode, 1.4.1, the hydrogen half cell is now replaced with an MM2 plus half cell. The cell notation of this cell is and we're given the cell notation of the cell. Okay, well, this is our anode and this is our cathode. What is the initial reading on the voltmeter? It is given as 2.05 volts. And the first question, identify metal M. Show how you arrived at the answer. What information do we have? We know that the initial EMF of the cell is 2.05. We also have the reduction potential of X. We calculated it in 1.3.2. That is minus 0.31. We're trying to identify metal M. If we find the reduction potential of metal M, then we're going to be able to go to our standard reduction potential table and see which one it is with ease. So the potential of M is what we are interested in. So what can we say now? We can say that the reduction potential, not the reduction potential, but the EMF of our cell is equals to the reduction potential at the cathode minus the reduction potential at the anode. So the reduction potential of the cell, 2.05. That at the cathode we have X. So that is going to be minus 0.31 minus the reduction potential at the anode. So we take in minus 0.31 to the left hand side. We're going to have 2.36 being equals to minus the potential at the anode. If we divide both sides by minus 1, the potential at the anode will be equals to minus 2.36 volts. If we go to our table of standard reduction potentials, at the anode we have magnesium or Mg. That is our answer to 1.4.1. 1.4.2 is the cell reaction exothermic or endothermic. In a galvanic cell, the reaction will always be exothermic. Right, 1.5. The reading on the voltmeter becomes 0 after using this cell for several hours. Give a reason for this reading by referring to the cell reaction. Well, the cell reaction reaches equilibrium. That is why the reading on the voltmeter becomes 0 after some time. Besides concentration, write down 2 conditions needed for the hydrogen half cell to function under standard conditions. In total, we have 3 standard conditions, one being concentration at 1 mole per decimeter cube. 1.1, we're looking for the other 2 standard conditions. That is pressure. Pressure is one of our standard conditions at 101.3 kilopascals. Another standard condition we have is the temperature at 298 kelvins or 25 degrees Celsius. That is the answer to 1.1. Let's go ahead and take a look at 1.2. Give 2 reasons besides being a solid why platinum is suitable to be used as an electrode in the above cell. So as you can see here, where there is hydrogen gas, platinum is used as an electrode. Let's talk about why that is so. Hydrogen gas, as the name says, hydrogen gas. So it is a gas and we need our electrode to be a solid. But apart from platinum being a solid, what other properties does it possess? Platinum does not react with H+. So that is one of the reasons why it is being used as an electrode. And another reason is that platinum is a conductor. Platinum is a conductor. At 1.3, we're supposed to write down the name of component Q. This is a galvanic cell and component Q should be a salt bridge. So there we go. We have a salt bridge in 1.3.1. and 1.3.2. What is the standard reduction potential of the X half cell? Right, this is for 1 mark. And when you are familiar with this kind of questions, you're going to be able to answer it without any difficulties. But here we sort of have to take the long route so I can show you what is happening. Let's look at the information we have. We are told that the initial EMF that is registered is 0.31 volts. So the EMF of our cell initially is 0.31 volts. Right, now let's look at our setup. This is the positive electrode and this is the negative. In a galvanic cell, the positive is the cathode and the negative is the anode. So what are we saying? We're saying that the potential of our cell can be determined by saying the potential at the cathode minus the potential at the anode. So what is the potential of the cell? This is 0.31 being equals to the potential at the cathode. The potential at the cathode is the potential of the hydrogen gas, as we can clearly see that it is at the positive terminal. So we're going to have 0. If you look at your table for standard reduction potentials, the potential of hydrogen gas is 0 minus the potential at the anode. So minus the potential at the anode, which happens to be X. If you go ahead and find the reduction potential of X, you're going to realize that it is equals to minus 0.31 volts. So this is the answer. It is for 1 mark because it is easy to see without doing any calculation. But if you are not familiar with galvanic cells and the EMF of a cell, this is how we get to the answer. Right. 1.3.3, the half reaction that takes place at the cathode. The cathode is the positive terminal on our galvanic cell. So we have the hydrogen gas. The basics at the cathode is where reduction occurs. What is reduction? Reduction is the gaining of electrons. So we're going to have 2H plus 2 electrons to give us hydrogen gas. This is the equation you find on your table of standard reduction potentials. If this was the anode, then we would write the equation in the following way. We would have hydrogen gas giving us 2H plus 2 electrons if it was at the anode. If it is the cathode, if it is at the cathode and the reduction is taking place, then this is our equation. Right. I'm just doing that for the sake of clarity. When you have a question which requires the half reaction at the anode. 1.4.1, the hydrogen half cell is now replaced with an MM2 plus half cell. The cell notation of this cell is and we're given the cell notation of the cell. Okay, well, this is our anode and this is our cathode. What is the initial reading on the voltmeter? It is given as 2.05 volts. And the first question, identify metal M. Show how you arrived at the answer. What information do we have? We know that the initial EMF of the cell is 2.05. We also have the reduction potential of X. We calculated it in 1.3.2. That is minus 0.31. We're trying to identify metal M. If we find the reduction potential of metal M, then we're going to be able to go to our standard reduction potential table and see which one it is with ease. So the potential of M is what we are interested in. So what can we say now? We can say that the reduction potential, not the reduction potential, but the EMF of our cell is equals to the reduction potential at the cathode minus the reduction potential at the anode. So the reduction potential of the cell, 2.05. That at the cathode we have X. So that is going to be minus 0.31 minus the reduction potential at the anode. So we take in minus 0.31 to the left hand side. We're going to have 2.36 being equals to minus the potential at the anode. If we divide both sides by minus 1, the potential at the anode will be equals to minus 2.36 volts. If we go to our table of standard reduction potentials, at the anode we have magnesium, or Mg. That is our answer to 1.4.1. 1.4.2 is the cell reaction exothermic or endothermic. In a galvanic cell, the reaction will always be exothermic. Right, 1.5. The reading on the voltmeter becomes 0 after using this cell for several hours. Give a reason for this reading by referring to the cell reaction. Well, the cell reaction reaches equilibrium. That is why the reading on the voltmeter becomes 0 after some time. A piece of zinc is placed in a test tube containing acidified MnO4-. After some time, it is found that a redox reaction has taken place. Use the table of standard reduction potentials to answer the following equations. Write down the name or formula of the reducing agent. On your table of standard reduction potentials, you have your reducing agents on the right and your oxidizing agents on the left. It should be easy to see that the reducing agent is zinc. Why are we saying that the reducing agent is zinc? That is the equation in 8.1.2. So let's go ahead and address that. When we look at zinc 2 plus and MnO4 minus, MnO4 minus is a stronger oxidizing agent, so it will undergo a reduction, meaning that zinc, on the other hand, the piece which is on the right hand side, it's our stronger reducing agent. It is going to undergo oxidation to form zinc 2 plus 2 electrons. That is 8.1.2. Let's take a look at 8.2 and 8.2.1. So we have a standard electrochemical cell, and the first question is to write the function of component Y. Component Y is a salt bridge. There's a few things that the salt bridge does for an electrochemical cell. One, it completes the circuit. It also provides a path for movement of ions. That is just some of the functions of component Y, a salt bridge. 8.2.2, in which directions will electrons flow in the external circuit? Choose from Ni to Mi, Mi to Ni. It means that now we need to determine whether Ni or Mn is the anode or the cathode. We have to go back to our table of reduction potentials. Mn is a stronger reducing agent. So this is where oxidation takes place, and we know that oxidation takes place at the anode. While on the other hand, Ni will be our cathode. In a galvanic cell, the anode is negative and the cathode is positive. Even though current flows from positive to negative, electrons flow from negative to positive. So that is the direction of flow of electrons, Mn to Ni. 8.2.3, we're supposed to calculate the initial EMF of the cell. So let's go ahead and do that. The initial EMF of the cell will be equals to the reduction potential at the cathode minus the reduction potential at the anode. At the cathode, we have Ni with a reduction potential of minus 0.27 minus the reduction potential at the anode where we have Mn, that is minus 1.18. If you put that in your calculator, you should get 0.91 volts. This is quite an easy one. Right, 8.2.4. Write down the balanced equation for the net reaction taking place. Let's start with the anode where oxidation takes place. At the anode, we have Mn. So we're going to have Mn losing 2 electrons to form Mn2 plus 2 electrons. And then at the cathode, we have Ni2 plus 2 electrons to give us Ni. It is easy to see that in equation 1, we have a loss of electrons. And in equation 2, we have a gaining of electrons. So in order to find the net cell reaction, we add the left-hand sides of the two equations and the right-hand sides of the two equations. But what we can do, we can ignore the electrons. We have 2 electrons on the left and the 2 electrons on the right. They're just spectators. We're gonna ultimately have, so we're adding Mn and Nn2 plus. So we're gonna have Mn plus Ni2 plus to give us Mn2 plus Ni. So Mn2 plus Ni. This is the net cell reaction. 8.2.5. The concentration of Ni to the 2 plus is now increased. Will the reading of the voltmeter increase, decrease, or remain the same? Okay, let's go ahead and make sense of this one. The initial EMF of the cell is given by the reduction potential at the cathode minus the reduction potential at the anode. We have an increase of Ni2 plus, the concentration at the cathode. So if you increase the concentration at the cathode, then this reduction potential is gonna increase. If that reduction potential increases, it is easy to see that the reading on the voltmeter will also increase. But let's say, for instance, it was the concentration of Mn2 plus that was increased. Then the reduction potential at the anode would increase. And if the reduction potential at the anode is increasing, the reading on the voltmeter would decrease. But in our case, the reading on the voltmeter is increasing. Is the reaction that occurs in this cell spontaneous? Write down only yes or no. Give a reason for the answer. That is 8.1, Prelim 2023. Let's take a look and see what is happening. So a galvanic cell is set up using an Mn and an unknown metal X. The initial EMF measured under standard conditions is 1.05 volts, as we can clearly see there. The electrons flow from the Mn to metal X in the external circuit, right? And then 8.1 is the reaction that occurs in this cell spontaneous. Yes, it is. And why do we say so? EMF is greater than 0. If the EMF in this cell is greater than 0, then the cell is spontaneous. This reaction does not need any external energy for it to occur, right? Does not need anything. It does not need power supply, unlike in an electrolytic cell. That is 8.1. Taking a look at 8.2, which electrode X or Mn is the anode. Okay, so the answer to this question is here in this statement. The electrons flow from the Mn to metal X in the external circuit. So we need to recall our basics with regards to a galvanic cell. The electrons, they flow from the anode to the cathode in the external circuit. So if they flow from Mn to metal X, then Mn should be the anode, and then the metal X should be the cathode. Clearly, the electrons flow from Mn to metal X in the external circuit. So Mn is the anode and X is the cathode. Okay, we just applying the basics here. That is 8.2, 8.3. Use calculations to identify metal X. So we are given the initial EMF, which is said to be 1.05. But obviously, using our table of standard reduction potentials, we can obviously find the potential at the anode, which happens to be our cathode. So at the cathode, this is where we have our metal X. This is where we have X. And then at the anode, that's where we have Mn, like we've deduced. So now let's go down and look for our table of standard reduction potentials. We can use table 4a, we can use table 4b, all is well, right? There's no difference really. So let's go ahead and look for Mn and see where it is. So let's take a look. Mn, where do we find it at? We have Mn right there. So the reduction potential at the anode is minus 1.18. Okay, and then we know that the EMF of the cell is given by the reduction potential at the cathode minus the reduction potential at the anode. Okay, so the reduction potential at the cathode, that is where we have our metal X, right? So the potential of X. And then at the anode, we have minus 1.18. So 1.05 will be equals to the reduction potential at X plus 1.18. Okay, so the reduction potential at X will be equals to 1.05 minus 1.18. So that's more like saying 5 minus 18. So we get minus 0.13 volts as our reduction potential at the cathode. So still sticking to the table of standard reduction potential, it should be easy to see that at the cathode, if the reduction potential is minus 0.13, we must have PB. We can clearly see there that the reduction potential is minus 0.13. So right, X is PB. We can clearly see that. Right, that is 8.3. Let's take a look at 8.4. Right, 8.4.1. Write down the two standard conditions for this cell. Okay, we know fully well that we need the temperature to be 25 degrees Celsius, right, or 298 kelvins. That's one of the conditions that we need. Another condition we need is concentration to be 1 mole per decimeter cube. These are our standard conditions. Okay, 8.4.1. 8.4.2. On the other hand, we are looking for the cell notation. Okay, so obviously we know that we have what is happening at the anode, the salt bridge, and what is happening at the cathode, essentially. So at the anode, we have Mn, like we talked about, right? So we're going to have Mn, the metal, and then Mn to the 2 plus the salt bridge, and then Pb to the 2 plus, and then we have PB. Okay, we can show the states here that is a solid, that is also a solid, and here we have aqueous solutions, right? We can show the states. Yeah, we can even go further to show the concentration also, that the concentration of these aqueous solutions should be 1 mole per decimeter cube. Okay, that is 8.4.2. 8.4.3, reduction half reaction. Reduction half reaction. So reduction occurs at the cathode. That's where we have a gaining of electrons. So we're going to have Pb to the 2 plus, that gains 2 electrons to become Pb. There we go. Nothing complicated there whatsoever. That is the reduction of reaction. And then if the question was looking for the oxidation of reaction, we would have Mn giving off 2 electrons to become Mn to the 2 plus 2 electrons. And then we can sort of combine these two into overall cell reaction, right? To get Mn plus Pb to the 2 plus, giving us Mn to the 2 plus Pb. This will be the overall cell reaction. But anyway, stories. A learner conducts 2 experiments to determine the reaction between copper and silver nitrate. In experiment 1, the learner adds a small amount of copper to a test tube containing silver nitrate. The solution changes from colorless to blue after a while. The first question, 2.1, we're supposed to define the term oxidizing agent. The oxidizing agent undergoes reduction. What is a reduction? Reduction is the gaining of electrons. So the oxidizing agent is a substance that gains electrons, or rather a substance that is being reduced. That is the answer to 2.1. Let's take a look at 2.2. Explain why the solution turns blue by referring to the relative strength of the oxidizing agents. So let's go ahead and compare copper 2 plus, and silver plus. Let's go ahead and compare these two by referring to the relative strength of the oxidizing agents. Ag plus is a stronger oxidizing agent compared to copper 2 plus. We're going to have copper losing 2 electrons to form copper 2 plus. And this copper 2 plus is where the color blue is coming from. The color of copper 2 plus is actually blue. Let's take a look at 2.3. Experiment 2. So in experiment 2, the learner now sets up a galvanic cell as shown below. The cell functions under standard conditions. 2.3, write down the energy conversion that takes place in this cell. We know the energy conversion that takes place in a galvanic cell. That is chemical energy to electrical energy. Anyway, stories. Let's go ahead and take a look at 2.4. In which directions will N ions move in the salt bridge? Before we answer any of those questions, let's determine first whether copper or silver will be the anode or the cathode. Just like we have already deduced in 2.2, copper is going under oxidation. It is getting oxidized. Oxidation occurs at the anode. So this is our anode and this is our cathode. Now we can answer our questions. 2.4, in which directions A or B will N ions move in the salt bridge? So N ions, they move towards the anode, and cat ions move towards the cathode. It is easy to see that the N ions are moving towards A. 2.5, calculate the EMF of the above cell under standard conditions. So the EMF of the above cell under standard conditions, we're going to have the reduction potential at the cathode minus the reduction potential at the anode. This is equals to, at the cathode, we have silver. What is the reduction potential? 0.8 minus the reduction potential of copper 2 plus. That is, you have to make sure that you're picking the right one because there's a few coppers on your table of standard reduction potentials. It is 0.34. If you put this in your calculator or you just compute it in your head, you shall get 0.46 volts as the initial EMF of the cell above. That is 2.5. Let's take a look at 2.6. Write down the balanced equation for the net reaction that takes place in this cell. Well, at the anode, we have copper getting oxidized to copper 2 plus 2 electrons. And then at the cathode, we have silver plus an electron to give us silver. Oxidation half reaction, reduction half reaction. If you look at the oxidation half reaction, we have 2 electrons. If you look at the reduction half reaction, we have 1 electron. So what you want to do in a case like this is to multiply out by 2 where you have only 1 electron. So let's go ahead and do that here at the cathode. We're going to have 2 Ag plus 2 electrons to give us 2 Ag. You're going to see right now why I'm saying we should do that. Now, when you have these 2 equations, what you need to do is to add the left-hand sides together and you add the right-hand sides. Let's go ahead and do that. If we do that, we're going to have copper plus 2 Ag plus 2 electrons to give us copper 2 plus 2 electrons plus 2 Ag. In a case like this, we call these electrons spectators. They're not taking part in our reaction. So we can drop them and be left with Cu plus 2 Ag plus to give us Cu2 plus 2 Ag. And this is our overall reaction. In an exam situation, this is what is needed. All of this junk is just me trying to show you how it comes about. 2.7, how will the addition of 100 centimeter cube of 1 mole per decimeter cube of silver nitrate solution to the silver half cell influence the initial EMF of the cell? Write down increase, decrease, or remain the same. In our standard conditions, with regards to the concentration, we need the concentration to be 1 mole per decimeter cube. So this change is not changing our standard conditions because the concentration is still 1 mole per decimeter cube. So the initial EMF will remain unchanged. The answer here is remains the same. What type of reaction takes place in this cell? Well, it is a galvanic cell. So the reaction taking place is a redox. Why are we saying it is a redox? That is because there is a transfer of electrons. Let's look at 3.2. Which electrode, P or Q, is magnesium? Give a reason for the answer. So let's go ahead and look at our electrodes. We have electrode P and electrode Q. P is negative and Q happens to be positive. In a galvanic cell, the negative electrode is where you find your anode. On the other hand, the positive electrode is where you find your cathode. Between magnesium and lead, which one is undergoing oxidation? Which one will be our anode? We need to go to our table of reduction potentials and determine which one is a stronger reducing agent. Magnesium is a stronger reducing agent. It is going to be electrode P as it is negative and consequently the anode. So the reason we have to give here is that Mg is a stronger reducing agent. So between magnesium and lead, magnesium is a stronger reducing agent. Let's take a look at 3.3, 3.3.1. Write down the following, the standard conditions under which this cell functions. This is a galvanic cell. We have 3 standard conditions. Well, one being the temperature at 25 degrees Celsius or 298 kelvins. Another condition is the concentration at 1 mole per decimeter cube. Lastly, we have the pressure. But pressure doesn't apply in our case in this cell. That is because we don't have any gas. So in this cell, we're supposed to only mention temperature and concentration. That is another trick you have to be aware of. Right. 3.2. We're supposed to write the cell notation for this cell. As soon as the question says cell notation, salt bridge, and then I can start thinking about all the other things. We know fully well that we're going to have the anode at the left-hand side and the cathode at the right-hand side. The anode is magnesium, so we're going to have magnesium 2 plus, and the cathode is lead, so we're going to have Pb 2 plus and Pb. And just like that, we have our cell notation. 3.3. Name or formula of the oxidizing agent in the cell. The oxidizing agent is the species that gains the electrons, that is experiencing a reduction. Well, in our case, the oxidation half reaction, we're going to have Mg giving us Mg2 plus 2 electrons. This Mg is our reducing agent. And on the other hand, the reduction of reaction, we're going to have Pb2 plus plus 2 electrons to give us lead. This lead 2 plus is our oxidizing agent. It is the substance that is gaining electrons. So this is our answer to 3.3.3. Lead ions. The following question, 3.4, we're supposed to calculate the EMF of the cell above under standard conditions. Right, the EMF of the above cell will be equals to the standard reduction potential of the cathode minus the standard reduction potential of the anode. At the cathode, we have lead, and the lead has a standard reduction potential of minus 0.13 minus the standard reduction potential at the anode. At the anode, we have magnesium, that is minus 2.36. If you put that in your calculator, you should get 2.23 volts as the initial EMF of the above cell under standard conditions. The tricky questions, 3.5. How will the voltmeter reading change if the size of electrode P is increased? So increasing the size of an electrode does not affect the EMF. So the answer to 3.5.1 will be remains the same. Right, and now let's take a look at 3.5.2. If the initial concentration of the electrolyte in half cell B is increased. So increasing the initial concentration of the electrolyte will increase the reduction potential of that space or of that electrode. So let's take a look at our equation. The EMF of our cell is equals to the potential at the cathode minus the potential at the anode. We are increasing the concentration in half cell B. Half cell B is where we have our cathode. So the potential at the cathode is increasing. If the potential at the cathode is increasing and the potential at the anode remains the same, then the initial EMF of the cell is going to increase. So the answer here is increases. Yeah, when we increase the concentration, the reduction potential increases, and when we decrease the concentration, the reduction potential decreases. But you cannot just say that EMF will increase because concentration is going to increase. You have to look at, is it the concentration at the cathode, or is it the concentration at the anode that is also going to matter. Learners are given two half cells, half cell 1 and half cell 2. During an investigation to identify the two half cells, the learners connect each half cell alternately to a cadmium half cell under standard conditions. We have the results for the first combination and the second combination. The first question, 4.01, write down 3 conditions needed for these cells to function as standard cells. Well, the pressure at 101.3 kilopascals. Another condition is the temperature at 25 degrees Celsius. And lastly, we need the concentration at 1 mole per decimeter cube. This is our 3 standard conditions. Let's go to 4.2, 4.2.1. For the first combination, let's identify the anode of the cell. So in our first combination, we are given the net cell reaction. Well, we have cadmium losing 2 electrons to form cadmium. So that is our anode. Our anode is cadmium. So we're going to have that there. At the anode, oxidation occurs. There's a loss of electrons. And as we can see, cadmium loses electrons in our first combination. And 4.2.2, we're supposed to identify Q using a suitable calculation. Well, what information do we have? We have the EMF of our cell. It is equals to 0.13 volts. We have the standard reduction potential of cadmium. It is equals to minus 0.4. So in order for us to determine Q, we're going to say that the EMF of our cell will be equals to the reduction potential at the cathode minus the reduction potential at the anode. So we're going to have 0.13 being equals to the reduction potential at the cathode. At the cathode is where we have Q, as we have already deduced that the anode is cadmium. And the reduction potential of cadmium, that is minus 0.4. So we're going to have 0.13 being equals to the reduction potential of Q plus 0.4. It should be easy to see that the reduction potential of Q will be equals to 0.13 minus 0.4, which is just equals to minus 0.27 volts. So Q is nickel if you go to your table of standard reduction potentials. Right, that is 4.2.2. That is how we solve those kind of questions. Let's go ahead and take a look at 4.3. So in 4.3, we're interested in our second combination. And 4.3.1, the oxidation of reaction. Well, what happened in reaction 1 is still happening in reaction 2. Cadmium is losing electrons. So that is our oxidation of reaction. We're going to have cadmium giving us cadmium 2 plus 2 electrons as our oxidation of reaction. That is 4.3.1. Let's go ahead and do 4.3.2. Name or formula of the metal used in the cathode compartment. Cadmium is our anode, so our cathode is R2, which happens to be a gas. If we have a gas, our electrode is going to be platinum. That is 4.3.2. The last question, 4.4. Identify the following species in order of increasing oxidizing ability. So the oxidizing agent undergoes reduction. We need to know that. So let's take a look at this. Between Q to the 2 plus and CD to the 2 plus, Q to the 2 plus is a strong oxidizing agent as it goes under reduction. So we know that Q to the 2 plus is a stronger oxidizing agent compared to CD2 plus. If you look at our second combination, we can come to the conclusion that R2 is a stronger oxidizing agent compared to CD2 plus because it also undergoes a reduction. The only thing that we now have to figure out is which one is a stronger oxidizing agent between Q to the 2 plus and R2. With cadmium, Q to the 2 plus and R2 act as our cathode. So whatever oxidizing agent between these two will lead to a higher EMF will be our strongest oxidizing agent. And if you look at the cell potential, R2 is giving us the highest cell potential. So we can say that CD2 plus is the weakest, followed by Q to the 2 plus. And the strongest oxidizing agent is R2.